Okay, guys, so this video, we want to take the next step. We've talked about some basic scenarios and calculating external forces. Before we go too deep into the internal forces, I want to give you an idea of some of the basic skills that you need to have in order to calculate internal forces and in particular forces on particular members within a triangular truss. So the first thing we want to take a look at here, we want to find components of diagonal forces, or in other words, we want to find the amount of force that's applied in the x and y directions given a particular force vector. All right, so we want to take a force and break it down into its most basic components, and in order to do that, we've got to look at that component form of a vector. Just as a review, the component form looks like this. Component form of a vector. This first thing here, this entry right here, is going to give us the magnitude or amount of force in the x direction. And this guy over here, y, is going to give us the amount of force being applied in the y direction. So hopefully I'll give you a couple quick examples, and hopefully that'll clarify things for you here. So we've got 50 newtons of force being applied directly downward on an object for this particular thing. So 50 newtons of force being applied directly downward. That vector would look something like that, directly downward, and that has a magnitude of 50 newtons. So if we're going to write this in component form, we want to look at how much of that 50 newtons is being applied in the x direction, or in other words, look at how much this is going left and right. And if I'm going to write the component form, well, this thing's going directly down, so 0 out of that 50 newtons is being applied in the x direction, or left and right. If you're pushing straight downward on something, all of that 50 newtons is going to be applied downward. So the component form for this particular thing is 0, negative 50. All right, another quick example here. 35 newtons of force is being applied in an effort to move the object or move an object to the right. So first of all, let's draw a little object. And whenever we draw a little object, we draw what's called the center of mass. We just put a dot right in the middle of it. And then from there, we can kind of draw in our vectors. So 35 newtons applied in an effort to move the object to the right, maybe a little bit different than what we've done in the past or what you've seen in the past. But when we draw these forces relative to the object that they're being applied to, we actually start from that center of mass, that center point, and draw it in the direction that it's being applied. So we don't apply the force that actually comes to that center of object. We stem from the center of object, or center of mass, out from that particular thing. So here's my little diagram that's going to model this scenario, and we'll talk about this diagram a little bit more specifically in a minute. But I need to figure out the component form. So how much of that 35 Newton force is being applied in the x direction? Well, it's directly in the x direction. It's not going up and down. So all 35 of it, and in particular, it's in the positive x direction. So all 35 newtons is in the x, 0 is in the y, and there's my component form. So let's look at one that's a little bit more interesting. So we want to know how much in the x and how much in the y, and this particular one has a direction of 30, so it's not directly up and down or left and right. We've got a 20 Newton force and a direction of 30, so that's going to look something like this, maybe. 20 newtons, and I can draw my line over. That represents the horizontal. So here's my horizontal axis. Let's give that a dotted line just so everybody has a good idea. It's not an actual vector. And lastly, we want to make sure that we label our direction. So we have a direction of 30 degrees right here. So essentially what I want to know is of this 20 newtons right here in magnitude, how much is in the x and how much is in the y? And if we use triangles to model this, I can figure that out relatively easily. So we drop down in altitude, creating a right triangle. This distance right here is going to tell me how much of that 20 newtons is being applied in the x direction, and this distance right here is going to tell me how much of that 20 newtons is being applied in the y direction. And not necessarily how much of the 20 newtons, but just how much is being applied in the x and how much is being applied in the y. So let's check this out. So I need to figure out if this has a length of 20 newtons, then how much is being applied in the x direction. And I can figure that out using my basic SOHCAHTOA trigonometric function. So I want to figure out the adjacent relative to the 30-degree angle. So that's going to be cosine. So cosine of 30 equals x over 20. So a couple different ways that we can do this. We can, when we go through and solve for x, we can write it and just leave it in this form. 20 times the cosine of 30 equals x. So I can write my component form. When I come up here to write my component form, I can either write it as 20 times the cosine of 30, which in particular situations in physics, it makes sense to do this. Or I can go ahead and simplify this and find an explicit number or answer for the number of newtons being applied in the x direction. Okay, so we plug that number into our calculator, and that spits out a 17.32 is about the number of newtons in the x direction, or the force that's applied in the x direction. So let's go ahead and figure out our y. Relative to this 30-degree reference angle, our y is opposite, so I want the sine function. So sine of 30 is going to be equal to my y component over the magnitude of the hypotenuse. Go through and solve. We have 20 sine of 30 equals y, and again, we can leave that in that form if we want to, and that's good for particular applications. So one of my component forms looks like this. I can also go ahead and plug that number into my calculator, so let's go ahead and do that. And what that spits out is 10. So the other way that I can write this is my component form looks like this: 17.32, comma, 10. So I have 17.32 newtons of force being applied in the x direction, 10 newtons of force being applied in the y direction. And notice that this does not equal 20. It's not going to give you, when you add these two together, it's not necessarily going to give you your 20 newtons. All right, so that's one thing that we want to make sure that we recognize. Okay, so one more example of this. We want to write the component form of a 15 Newton force being applied in the direction of 125. So let's go ahead and model that scenario. First thing, let's get some axes on here. So I've got my axes on here. Let's see here. So here's my vector. It is 15 newtons being applied in a direction of 125. So this thing's going to look probably something like this. Remember, 125, we're going to start at the x-axis. We're going to wrap that around, so we hit 90 right here, and then we need an additional 35 degrees to get to where we need to be. So let's go ahead and label that. If this is 35, the complement of 35 would be 55. So we know that this angle is 55 degrees. And the reason that I'm labeling that angle is because I'm interested in this y component and this x component. Okay, so there's my x, there's my y. Let's see what else we need here. We've got to label our 15 newtons. So we got 15 newtons right here. So if we want to find the x is the adjacent, so we're looking at cosine of 55 is equal to x over 15. So 15 times the cosine of 55 is going to be the x component of this 15 Newton force in the direction of 125. Go through and solve for the y. Relative to that reference angle, we've got opposite, so this is going to be the sine function. So the sine of 55. And notice that the y function, or the y component, is always related to the sine function. The x component is always related to the cosine function. So sine of 55 equals y over 15. Go through and solve, and you got 15 sine of 55 is going to be equal to y. So again, if we want to keep it like this, we can write our component form as 15 cosine of 55, comma, 15 sine of 55. That's perfectly acceptable. And if we look back at the last example, notice again, there is a pattern emerging here. These two distances look exactly the same, except for the x component, we've got the cosine function. For the y component, we've got the sine function. So there's definitely something to that. I don't want to delve too deep right now, though. If we want to write that in a little bit more explicit form, we got to plug these numbers into our calculator. So we get 15 cosine of 55 is equal to about 8.60. And 15 sine of 55 is going to be equal to about 12.29 or 12.3. So there's your component form. And again, what this is telling us, just to give us a general idea, is that this 15 Newton force in this particular direction actually applies 8.6 newtons of force in the x direction and 12.3 newtons of force in the y direction. Now, there's one thing I actually have to fix on here, and this is really important that we pay attention to. In the x direction, notice we're going in the negative x direction, so this should actually be a negative component here, negative x component. So this indicates that we're going to the left 8.6, or to the left 15 cosine of 55 units. So make sure that that's something that you pay attention to here. The y direction is okay the way that we have it. It's at 12.3 in the positive y direction. So we're good there. Okay, so the next thing that we want to check out here is constructing free body diagrams. And really, guys, all these these give us the ability to visualize the forces acting on a particular object. All right, so this is how we construct things in order to create a visual of what's going on, so that we can then use our math to solve for particular forces. Okay, so these are called free body diagrams. You can see a couple examples of those there. We've got an object, in this case, a 10 kilogram weight, and you can see these 4 different forces acting on that object. And that's all these things are, is we're gonna plot every single vector or every single force that's acting on that object in a particular situation. Very similar to what we did with those flat bridge examples. Here you've got an incline, and we'll talk a little bit more specifically about this one. But this thing is inclined. You've got one force acting here, the force of gravity, the normal force here, and then another one that kind of balances things out. So let's take a look at a couple scenarios. So number one, you've got a book resting on a table. Here's a book. Here's a table. Very fancy drawing here. So my book, again, we're going to use this thing called the center of mass. It's really just put a point in the middle of the object. All right, and from that point are going to be all of the different forces that are acting upon this object. So construct a free body diagram that models a book resting on a table. So book resting on a table, we know that gravity acts downward on that particular book. So we label that F sub G for the force of gravity. And then my next force, because it's resting, it's at rest, we know we've got an equal and opposite force that balances that out, and that is what we call the reaction force, or in physics they call it the normal force. So they label that a lot of times F sub N, the normal force. It's really a reaction force due to gravity. That's all it is. Reaction force due to gravity. All right, so there's our free body diagram. This is really all there is to it. There are only two things acting on this particular object, so we label those two things, use that center point there, and all of our forces stem from that center point. Next one, what if a student tries to push that book to the right, but it doesn't move? Construct a free body diagram that models the scenario. So essentially what we have is the exact same thing that we modeled up here, but we're adding in another force. And that other force is a push. And specifically, it's a push to the right. All right, so somebody tries to push the book. They can't push that book. So let's model the push first. So our first force is, I don't know how much force is being applied, but we're going to, we'll just use that amount, and I lost my label here. So this is the normal force, or the reaction force. Down here we've got, they call it the force applied. So a lot of times, you know, if an object pushes on another object or applies a force on another object, they just call it the force applied. Now the key here is that it doesn't move. The book doesn't move, and so we know it's in static equilibrium, and under static equilibrium, if we've got a particular force applied in the x and it's not moving, then there better be a force that's equal and opposite acting in the other direction. And so we model that force. This is actually, in this particular scenario, this would be the force due to friction, because we know that we've got to push this book hard enough to overcome the amount of friction that's going to be on here, going to be applied. But this is just the force due to friction. And this makes sense within the context of static equilibrium. If you're trying to push something and it doesn't move, then that means that there's something else that's equal and opposite that's balancing that particular applied force out. All right, last thing we're going to take a look at, and that is the same book resting motionless now, not on a flat table, but on an inclined ramp. Okay, so we want to construct this free body diagram. Here's my inclined ramp. Here is my book. There's my center mass. And so we want to construct this free body diagram that models everything that's going on. So first and foremost, we still have that force due to gravity. And that force due to gravity doesn't care that this thing's on an incline. It's still going to act perpendicular to whatever the ground is. And so we kind of model this, you know, if we had the ground that is something like this, the force due to gravity is going to be perpendicular to the ground in this particular case. All right, so we need some other forces that kind of balance this out. Number one, we've got the reaction force of the table. If this thing sits motionless, that means it's not moving. So we're looking at static equilibrium here. So we need a reaction force from the table. And the reaction force from the table is going to be perpendicular to the table, not to the ground. So let's check out what that looks like. That looks something like this. So it is it's not directly up and down. There's a little bit of force acting in this direction, to the left direction. So this does, when you look at when you think about the x and y components of this force, this does have a little bit of force acting in the x direction, in the negative x direction, which to us is really important, because if this thing's not moving, if it's motionless, we need to balance that out. Okay, and we do that by drawing this arrow right here, this vector right here, and that would actually balance that out. All right, so we're not going to go too crazy deep into this. I really just wanted to touch on this topic of constructing free body diagrams. Let me throw some labels in here. This is the normal force, and this is, I don't know, we'll call it just force due to friction. Okay? So we've got constructing free body diagrams we talked about, and we also talked about this concept of finding the component form, or the amount of force that's being applied in the X and the Y direction for diagonal forces, such as this one.